Okay, welcome everybody. We're going to get started. So today I have the pleasure of introducing Dr. Drew Gronewold. He's an associate professor at the University of Michigan School for Environment and Sustainability. He also holds adjunct appointments in the Department of Civil and Environmental Engineering and Environmental Science at the University of Michigan. Drew conducts research through a range of hydrological science projects, and they all explore methods for quantifying and communicating uncertainties arising within long-term hydrologic monitoring networks and data, and incorporating those uncertainties into models and risk-based water resource management decisions. Much of his recent research has focused on monitoring, analyzing, and forecasting long-term water budget and water levels on the Laurentian Great Lakes. I've had the pleasure of working with Drew for the last 8 or 10 years or so, and I've always enjoyed his talks, and I'm glad he's here to share this talk with us today, and I hope you enjoy it. So we'll turn this over to Drew to get started.
All right, great. Tim, thanks so much. And just Tim, with the nodding of your head, can you hear me okay?
Yep.
Okay, great. I'll assume everyone else can as well. So thanks for the introduction, and thanks to the folks at Wayne State, particularly Jamie, Delashawn, and also Tim for helping host this and organize this. It's been really, really smooth getting things set up, so thank you. And thanks everyone for taking time out of the afternoon to have this presentation and discussion. So today I wanted to focus on the topic of understanding Great Lakes water level variability. I noticed there's some familiar faces in the audience, which is great, and there's also some new folks too. So looking forward to hearing your feedback, questions, and comments. So for the talk today, I first want to start off with just a few introductory comments, focused a little bit on our motivation for studying the Great Lakes, but also for a few other things that our research group is working on. But then I want to bring it back to some contextual points for studying the Great Lakes. And then look first at water levels, historical and current water levels, including an indication of some extremes. And then for point number 4, I want to take a look at what's happening with the Great Lakes hydrologic cycle. And this is really sort of one of the key points behind understanding why Great Lakes water levels are fluctuating and unraveling that mystery by looking at the hydrologic cycle. And then I want to leave you with just a few things that are going on right now, some collaborations and some research projects that we have going on that are related to this that I think you'll find interesting. So to begin with, I really need to start off by thanking a lot of folks, not just Wayne State University for hosting this, but members of my current research team. There have been some recent changes in this with the summer and some graduations, but this is the current group of postdoctorate fellows at the top, graduate students, and then a great cohort of undergraduate students that I'm currently working with in our group, which we call SEAS Hydro at the University of Michigan. And the work that I'm going to present here really would not be possible without this strong group of talented students. But I also want to mention that before coming to the university, I worked for the National Oceanic and Atmospheric Administration. And here is a sampling of many of the colleagues I worked with when I was at NOAA. Again, the work that you're going to see here, the foundational work on understanding water levels would not be possible without this cohort at NOAA, and then a lot of other collaborators and colleagues across other state and federal agencies around the region. And so to finish off that point, here are some of the agencies and partners that we're currently working with that are providing us with funding for our research, including the Army Corps of Engineers, the United States Geological Survey, the Great Lakes Protection Fund, the Michigan Department of Transportation, and the Conference of Great Lakes St. Lawrence Governors and Premiers, including a lot of generous funding from within the university itself. So to start off with, why study the Great Lakes? From a global perspective, what are some of the research questions that are motivating what we're doing here? Well, first off, the Great Lakes are an unbelievably complex and fascinating ecosystem, both from a water quality perspective and a water quantity perspective. And I feel like this satellite image underscores some of those points. This satellite image is taken from sort of a late fall, early winter, where ice is not yet formed on the lakes, but you can see a lot of clouds forming across the lakes here, sort of as a side parallel process along with water vapor transfer and evaporation. You can see the distribution of snow across the landscape. All of these processes are things that we try to understand and even represent in computer models when we understand the hydrologic cycle and also the water levels of the Great Lakes. Another point I want to make when about understanding of the Great Lakes here in our backyard is to put things into a global context. This table shows a summary of the largest lakes on Earth. So in this column, you have the name of each lake. Here are the country or the countries in which the lakes reside. And then we have a summary of the lake surface area, both in kilometers and miles squared, as well as the volume. And there are a lot of different points we could make about how water is distributed among these lakes, but here's the point I want to start off with for this talk. There are about 100 million lakes distributed across the Earth's surface, and they contain nearly all of the Earth's fresh surface water. So another way to say that is that when we look at fresh, unfrozen surface water, nearly all that water is stored in lakes. Rivers are relatively transient. There's an awful lot of water in groundwater. But again, from an unfrozen, fresh surface water perspective, nearly all of the Earth's water is in lakes, distributed about 110 million of those lakes. 80% of that water is in the lakes on this table. So again, 80% of all of the fresh, unfrozen surface water is in about 10 of the Earth's largest lakes. And so for that perspective, I think it's critical that we as a planet have a strong understanding of how water enters and leaves these large lake freshwater systems. Now, another reason we're compelled to understand this table and this flow of water through lakes is that this table is changing over time. Not long ago, Lake Chad would have been on this table, but if you can see from this paper that I'm highlighting here, the blue area sort of represents where water was within the Lake Chad boundary. So here's Lake Chad when it was filled in the 1950s, surface area of around 24,000 square kilometers. And then over time, due primarily to climate change, but also anthropogenic demands, the water has diminished in surface area to an order of magnitude less than what it used to be. So we think it's critical to understand how these large lake systems are changing. And we think using the Great Lakes in our backyard is a great sandbox for understanding that. There are also major issues regarding regional water demand. Right now, this article was just published in the Chicago Tribune on February 25th, taking a look at how groundwater sources are being depleted around the Great Lakes. And in the case here of Joliet, Illinois, this well was just sampled, and the plan is to transition from groundwater supply to a surface water supply. And this raises and underscores long-term questions about how communities straddling or adjacent to the Great Lakes Basin are going to be able to use surface water supplies as groundwater sources get depleted. This is a question that is not unique to the Great Lakes. It's a global question. And again, we have an opportunity to get ahead of addressing it here in the Great Lakes with an understanding of water levels. I want to mention that there's some other things that our research group does as well. We like to take a look at statistical approaches to understanding uncertainty and variability in a broad range of environmental systems. One of the areas where we've done work and we're continuing to do work is looking at things like changes in ice cover variability. And I want to show this slide that was published several years ago and distributed through the public media that has peak ice cover across the Great Lakes shown in the white dots, along with a yellow line that seems to indicate some long-term downward trend. And what I would offer to this group is that I would, as a statistician, challenge the integrity of that yellow line relative to the variability that we're seeing in ice cover behind that yellow line. And in fact, some of the research we've done on this looks at ice cover across the Great Lakes and fits alternative statistical models to it. So what you're seeing here are a series of 3 panels, 1, 2, 3, representing the western, central, and eastern portions of Lake Superior. And the black dots represent the duration of ice cover in each of the years starting 1972 all the way through the late 2000s. And what we did is we tried several different statistical models, including a linear trend, which is what's suggested by this slide right here, as well as a change point model, and then other models, including just simply no change. What we found in this particular study was that the best explanation for the changes in ice cover across this time period were not some linear trend like you see here, but actually a distinct change point. And this is critical from a management planning perspective. If things like ice cover or temperature or water levels are going to change through abrupt shifts rather than smooth trends, that's really important for how we make planning decisions going into the future. This work was published in Climatic Change in 2016, along with a series of other papers that looked at shifts in ice cover, as well as temperature and other regional variables. And then finally, another example of the research that we do in our research group that is not related to water levels, but some of you might find interesting, is using statistical models to understand water quality analysis variability. And we were called upon by a colleague, Mark Sobsey of the University of North Carolina at Chapel Hill, to use statistical models in water quality to develop a new testing kit. So what this image is showing is the results of this particular new sampling kit. It's called the compartment bag test, or CBT. And what we were able to do is we were able to design this testing kit to have 1, 2, 3, 4, 5 different compartments, each of a different volume. And with this test kit, someone can take a water quality sample, divide it up among these different pouches, and read the pattern of positive and negative bags in each one of these pouches. And then using a statistical model, we can develop a table like this one that tells us for any pattern of positive and negative bags, what the risk for water quality borne contamination is and threats to human health. So this was published in the Science of the Total Environment not long ago. And this bag actually formed the basis of a company called Aquagenex based in Chapel Hill, North Carolina. And this kit is being used all around the world. I mentioned this as an extension of some of the research we do, looking at how we quantify uncertainty in order to impact and improve water-related management decisions. But for the rest of my talk, let's focus in on, get back to the Great Lakes and Great Lakes water levels. And I want to start off with just a few contextual points that are important about the Great Lakes. I recognize some of you might study the Great Lakes for a living, some of you might not. So let's just make a few high-level key points here that are important. One point I want to make has to do with the magnitude of the lakes, and in particular, the magnitude of their surface area. So here's the table I showed earlier. What I want to do is highlight the lakes that constitute the Great Lakes, and we see some interesting patterns. One of which is that when it comes to surface area of fresh surface water, there's really no other system on Earth that comes close to the amount of surface area that we have here on the Great Lakes. That has important implications for how we study evaporation off the lakes and the impact on the hydrologic cycle, as well as the amount of precipitation that falls on the surfaces of the lakes themselves. Because there is such a large freshwater surface water body, those two factors are really important to the hydrologic cycle and to water levels. Another point I like to make is that in addition to the magnitude of the lakes, is the fact that they are bisected by an international border. So if you look at this image on the left, that's showing the lakes, as well as this hatched area, which is the typical boundary of what we consider to be the Great Lakes Basin. I've also added in here for reference the watershed of the downstream portion of the St. Lawrence River. And it's helpful to view the Great Lakes as part of a large river system that drains out through the St. Lawrence River, as well as a large lake system. But this slide is intended on the left here to show that the international border runs right down through the Great Lakes. And this has important implications for how regional scientists assemble and pull together data sets and models that can represent the system as a whole. The image on the far right here puts the size of the St. Lawrence and Great Lakes River Basin into context with the 20 largest river basins on Earth that are all highlighted in black here. So a lot of studies ignore the Great Lakes and when they look at large river basins, in part because it's hard to resolve the surface of the lakes, and also because it's hard to resolve data sets along the international border. And then a final point I want to make about the magnitude of the lakes is the total continental discharge that comes through the Great Lakes and St. Lawrence system. Very few people, I think, can understand and appreciate just the magnitude of flow that's going through the St. Lawrence River system. This is a ranking of the largest continental rivers in North America. So the largest is the Mississippi, and most people might guess that, which is with an annual average discharge of around 18,000 cubic meters per second. But the St. Lawrence is the second highest river discharge off the continent, followed by the Mackenzie, the Columbia, and the Yukon, and then these other large rivers in Canada. We think it's helpful to put the St. Lawrence River system into this context so that people on a continental and a global scale understand just how much water is flowing through the system. So let's talk now about water level extremes and look at the very robust and historical water level record. And I want to thank some of my students who have helped update and continuously publish this particular data record. that builds on records that are maintained by the US Army Corps of Engineers and NOAA, the National Oceanic and Atmospheric Administration. So what you'll see in this plot along the bottom here is a time scale that goes all the way back to 1860. So it goes from 1860 literally up to almost the current month. And then on the vertical axis here, we see surface water elevation in meters relative roughly to sea level. All of the vertical numbers here are scaled on a similar scale so we can compare apples to apples. And then for each lake or lake system, we have 3 data sets. We have a blue dot, a light blue dot, excuse me, that represents the monthly average water level. We have a dark blue dot that represents the annual water level, and then a red line that represents the long-term average. And I want to highlight a few time periods in this record. The first important time period in this record goes from 1860 up until about 1918. This is a time period where there was actually really only one gauge on each of the lake, and a lot of the federal agencies referred to that gauge as a master gauge. And there are a lot of complications with utilizing the water level record from that time period. One of the most important is the concept of isostatic rebound. So isostatic rebound refers to the rate at which the surface elevation of the land surface around the lakes is rising at a different rate in response to the loss of pressure from glaciers that receded during the ice age around 14,000 years ago. So if you think about a big Posturepedic mattress, a soft mattress, you put a big weight on it for a long time, and if you slowly lifted that weight off of the Posturepedic mattress, it would slowly start to rise. These numbers here that were published in a paper by Andre Mainville and Mike Kramer several years ago show the relative vertical velocities of the land surface around the Great Lakes. So to put this in perspective, if you look at this 0 line right here, that represents sort of a reference line of 0. The northern shore of the Great Lakes along Lake Superior and Lake Huron here is rising at a rate between 30 to 50 centimeters per century relative to that 0 line. In geological timescales, that is flying. So a half a meter per century of vertical land rise relative to this 0 line. If you look at these black dots, these are showing where there are either current or historical water level gauging stations. And you can imagine if there was only one gauge on a lake back in the period from 1860 to 1918, that gauge would be either rising or falling relative to the actual water level. And that's a challenge with using water level data prior to 1918. I also thought it would be helpful to add in this particular image, looking at isostatic rebound on a global scale. So these red areas indicate areas where glaciers have receded or permafrost has been melting in response to climate change, and the land surface is rising dramatically. I think this is an interesting image to look at because of all the places where you could study isostatic rebound, the Great Lakes is one of the trickiest, where there's a pretty strong gradient in the rate of surface elevation rise right here. Okay, so if we continue through the water level record, just to understand some of these historical extremes, another interesting time period is the early 1960s. This is a period where 2, I would say, important events have occurred. One is water levels were very, very low on the Lake Michigan Huron system, but also there were controls put on the outlet of Lake Ontario, as many of you know, in particular the construction of the Moses Saunders Dam designed to hold water in and modifications to periodically allow more water out. And you can see the overall dampening in the range of water levels on Lake Ontario in general after that 1960 project relative to the period before it. I also wanted to take a look, if you can, at the extremes across the entire system during these time periods. One thing you can see is that while water levels got very, very low here in the early 1960s, even on Lake Ontario, they did not get as low on Lake Superior, and we can talk more about that later on. I want to shift ahead here for context to the mid-1980s when water levels across much of the system were extremely high. One thing to note is that on Lake Ontario, they did not reach extreme highs the way they did across the rest of the system. And then we can shift here to this period of relatively low water levels that began in the late 1990s. During this time period, water levels were persistently low across the system, and in particular across the Lake Michigan and Lake Huron system. Monthly and all-time record lows were set, and there were concerns about a narrative of a future dominated by low water levels. And it's interesting to look back at the records and the media and the science from that time period to see just how strong the narrative was about future of water loss. There were even images that were put out on MLive and other media distributions like this one that show Lake Michigan on the left here and Lake Huron being replaced by this sort of massive drain, sort of implying that there's water being lost from the system, but we don't have a clear understanding of why. Most scientists did have an understanding of why, but there was a big question about what might be happening into the future. Another slide I want to show from that time period comes from a paper that was published in the Journal of Great Lakes Research that was looking at water level projections being made during that time period. And what you can see here is that for each of the lake systems represented by these different colored dots, this paper seemed to suggest that regardless of how far out you looked, water levels were bound to go down on each of the lakes. And what was very interesting is that this single image made its way into the National Climate Assessment during that time period, and I believe was blended into a broad narrative across the entire country of a future dominated by high temperatures, aridity, and drought. And for those of us who live in the Great Lakes, we can argue that planning around a future of aridity and drought is probably not particularly helpful. It certainly wasn't helpful for the next several years of water level management on the Great Lakes because water levels rose at an unprecedented rate. From 2013 to 2017, our research indicated that water levels on Lake Michigan, Lake Huron, and Lake Superior had never risen as quickly in the entire historical record. So we published some of this work in EOS, which is an outlet for the American Geophysical Union. Here's the cover story that shows water levels, or excuse me, water crashing over the iconic bike path here in Chicago. And here is coverage on a national scale from the New York Times, talking about how flooding downstream in Montreal is displacing thousands of homes, and a similar picture showing citizens pleading to Governor Cuomo to actually let more water out of Lake Ontario during that time period, which would exacerbate flooding in Montreal. So this was a big deal, the amount of extra water into the system. I'm sure most people on the phone have other stories or anecdotes about how the extraordinary water influx to the system impacted not just water levels, but other management practices. Let's take a closer look here at what exactly has been going on with the hydrologic cycle over the historical period of record. And we're going to focus on two time periods, a period of persistent lows, and then a period with this surge. So first off, just to make sure we're all on the same page regarding the major components of the hydrologic cycle, regional science find it helpful and conventional to divide up the entire Great Lakes Basin into the individual lakes so that we can account for the amount of water entering and leaving each of these basins, and then we can separately account for the amount of water transferring between the basins. So first, if we look on the left here, we can summarize the major water balance components within each lake basin. And generally, they can be divided into three categories. So if we look here at Lake Superior, on average, over long time periods, these three categories are first, the amount of water coming in through all the rivers and streams. That's represented by this green bar right here. And the number indicates that around 1,600 cubic meters per second of water come into Lake Superior on an annual average through rivers and streams. Interestingly, because Lake Superior and the other lakes have such a high surface area, more water comes into the Lake Superior Basin through precipitation on the lake surface itself. Around 2,000 cubic meters per second of water comes into the Lake Superior Basin directly through precipitation on the lake surface. Truly an extraordinary hydrological phenomenon that's hard to replicate anywhere else on Earth. And then the amount of water that's lost from the basin is represented by this pink bar here. It's representing evaporation, and the amount of water lost is about 1,400 cubic meters per second. The actual numbers may not mean that much to everybody, but the relative height of these bars are the same as we go across the entire system here. If we shift over to the right-hand side of this image, we can look at the rate of flow between each one of the lakes through what we often call the connecting channels. And we can see, just like any river system, flow accumulates as we go downstream. What I find very interesting is that as we reach the end here, the flow going out is around 7,000 cubic meters per second at the outlet of Lake Ontario. I mentioned earlier that if we move further downstream, the total flow on an annual average scale is around 10,000 cubic meters per second. So really extraordinary flow rates here. But the take-home message is that these are the major components of the Great Lakes water balance and of the hydrologic cycle that lead to changes in water levels. We've been doing a lot of research recently to sort of update the historical record. There's tremendous research that's been done over the past several decades. But in one recent paper that we came out with, led by my postdoctorate fellow Hong Do, along with Lauren Fry, who now works at the National Oceanic and Atmospheric Administration, is the use of a statistical water balance model to pull all different types of data sets together. Different data sets about evaporation that are developed by different countries and agencies, different estimates of precipitation, and pull them all together into a common framework to improve our estimates of the water balance components and their uncertainties. We just recently published this paper in Science, in Nature Scientific Data, and it's being used right now as a basis for a lot of other ongoing studies. But let's shift gears here for a second, and let's take a look at these two water level periods and see what was happening with precipitation, evaporation, and runoff during these two time periods. So first, let's think about this low water level period, particularly for Michigan, Huron, and Superior. And what I want to show you here is a time series of both water levels and precipitation. So I apologize, there is not a horizontal time scale on here, but this is actually showing water levels going all the way back to 1860. So on this axis, we have water levels. These blue dots are the actual annual water levels on each lake system. And then on this axis here, I'm showing total annual basin-wide precipitation in millimeters. And that's represented by these color bars. These represent total annual precipitation. The orange bars represent years where precipitation was below the long-term average, and the green bars represent years where precipitation was above the long-term average. So a couple key things that we've seen here about the relationship between precipitation and water levels. The first is that you can see over time, in a pattern that is consistent with global climate change models and scenarios, precipitation across the region has been consistently going up, and in fact, even almost shifted around this time period right here from below average to above average conditions. What you can also see is that throughout a lot of this record, water level variability tends to follow precipitation variability. As precipitation goes up, water level goes up. However, that pattern, there's a significant departure from that pattern in the late 1990s here, where you can see water levels plummeting on the Lake Michigan-Huron system without a corresponding decrease in precipitation. So if we think about the water balance during this time period, we might think that there's something else in the water balance might have changed, and that's exactly what happened. If I shift this slide from showing water levels with precipitation in the background, and I shift it to showing water levels with evaporation in the background, we get a clear understanding of what was driving water level variability during that time period. Here now we're showing evaporation, where red bars represent annual evaporation above the long-term average, and green bars representing evaporation below the long-term average. So what this period indicates is that a dramatic shift in evaporation led to these below average water levels. So now let's take a closer look at the water balance during this most recent period where there was a surge in water levels. And let's see if we can take a closer look at what was happening with the water balance. And I'm going to take some results from a paper we just recently published in the journal Geophysical Research Letters. What I'm going to do here, you haven't missed anything. There's no data being shown yet. I'm just going to start off with a blank plot to get things set up first. In the top set of panels here, I'm going to show what's happening across the land surface of the Great Lakes. And let me say that again, across just the land surfaces surrounding the Great Lakes. And in the bottom panels here, I'm going to show what's happening from the water balance on top of the lakes themselves. Each panel is going to have the same x-axis going from 1950 to present. So the first data set I want to show you on the top here are the data sets corresponding with the land surface. The first is what's happening over the land surface with precipitation, and then with water being lost off of the land surface through evapotranspiration, and then really here the net amount of water that eventually makes its way through either the surface or subsurface as runoff. I'm using this same coloring scheme where the colors represent either years above or below average, So what I want to point out here is first that precipitation on the land surface has been going up over time. This black bar here represents a 15-year rolling average window throughout the time series. So what we're showing here is that on the land surface, precipitation is going up, but so is evapotranspiration. And this is consistent with that narrative I talked about earlier about temperature going up, increased solar radiation, and water loss through evapotranspiration. And this is happening all across the country. In the Great Lakes, this is leading to sort of no real net change in runoff. We can see that this black bar doesn't have a real dramatic pattern to it, especially over the past several years. The past 5 years do have an increase in net runoff, but in a way, these two forces are balancing each other out. Precipitation going up, evapotranspiration going up. Now let's look at what's happening over the lake surfaces. What we see here in the precipitation over the lake surfaces is almost an amplification of this pattern, an extraordinary amount of precipitation coming into the region over the lakes over the past several years, even more than the anomaly in the land precipitation. But what I find fascinating is if we look at water loss patterns over the lakes over the past several years, they do not follow the same pattern as evapotranspiration on the land. In fact, what we see here is much more variability in lake evaporation, and in particular, a pronounced decrease in lake evaporation starting in 2013 and 2014. Much of this coincided with the cooling of the lakes that occurred with the outbreak of cold Arctic air in the 2014 Arctic polar vortex deformation. So when you add these two together over the lakes, the abundant precipitation, the loss of water loss or the decrease in water loss through diminished evaporation, the net amount of water that's entering the Great Lakes over the lakes themselves has been just extraordinary over the past 7 to 10 years. And that's represented in this diagram right here. So again, a very interesting, I think, way of looking at the water balance over the past several years, and in particular as a way to look at what's been happening with the surge in water levels. This most recent panel comes from this paper that I mentioned, Geophysical Research Letters. And because of the fact that precipitation and evaporation have opposite impacts on water levels, and because we see precipitation consistently going up, in a way becoming a stronger force on water levels, while at the same time, evaporation over time is expected to increase as well. And so we like to think of these two competing forces almost having a tug of war on water levels. They're getting stronger, and in some cases, one of those two forces might change suddenly due to an Arctic polar vortex deformation. And when it does, we can expect a significant swing in water levels. That's why we titled this paper, A Tug of War Within the Hydrologic Cycle of a Continental Freshwater Basin. So to wrap things up, I want to spend a few minutes talking about some of the related research that's going on with our group and some of our collaborators that connects to water levels and the water balance. The first is an exciting project that we have going on with the United States Geological Survey. I'm guessing a lot of you have probably been thinking as you've been watching this, wait a minute, what about groundwater? I would argue that the representation of groundwater in regional data sets and models has been a noticeable absence. We partnered with the United States Geological Survey to propose a project to what's called the United States Geological Survey's John Wesley Powell Center, named after John Wesley Powell. And through this project, we are specifically trying to improve the representation of groundwater in models and data sets. And we're actually looking at 3 different approaches. The first is we're trying to actually put groundwater into the water balance framework that I mentioned earlier, that statistical water balance model. We're also looking at land surface models and trying to understand how a better representation of groundwater fluxes and base flow in the state-of-the-art land surface models might improve land surface hydrological modeling. And then the final part is we're looking at what happens when you explicitly represent groundwater as a subsurface flux into Great Lakes 2-dimensional and 3-dimensional hydrodynamic models. Does it change pollutant fade and transport patterns? Does it change temperature dynamics, both at the surface and at depth? These are some of the key questions that we're answering through this exciting project with the United States Geological Survey. Another project that I want to mention that we have going on right now that's in close partnership and with funding from the Army Corps of Engineers is to better understand the uncertainty in these numbers right here. These flow dynamics through the connecting channels of the Great Lakes are huge. And what we're finding is that as we try to do things like add groundwater into our understanding of the hydrologic cycle, or even reduce uncertainties in things like Lake Erie precipitation and evaporation, what we're finding is that when we look at the Great Lakes basin water balance on a holistic scale, the uncertainties in these downstream water balance components are completely dwarfed by the uncertainties and the variability in our estimates of the connecting channel flows. In other words, if you have a slight error in the Niagara River flow, or a slight error or uncertainty in the water flowing out through Lake Ontario, it makes it very hard to distinguish the uncertainties in these internal water balance components with each one of these lakes, let alone to begin to understand the fluxes of groundwater. So we're embarking on a very exciting project with the Army Corps of Engineers and others right now to further quantify uncertainty in these channel flows and better represent them in holistic water balance models. Another exciting project that we have going on right now is working with regional partners to improve forecasting. What I'm showing here is a conventional representation of seasonal forecasting where we have, for Lake Michigan Huron, we have historical water levels in light blue dots right here. We have a long-term average water level in red. We have monthly maximum water levels here. But then these orange bars right here represent a conventional approach to expressing uncertainty in water levels over the next several months. And one of the research questions we think needs to be resolved is, to what extent are forecasts, and whether at the 6-month time scale or at the annual, interannual time scale, to what extent are they impacted by, and are they able to represent phenomena like an Arctic polar vortex deformation? So this schematic is showing what happens when, on the left, we have a polar vortex that is stable. The very, very cold, dry air is contained to the northern, to the Arctic. But if we have a weak jet stream and this polar vortex becomes wavy, that cold Arctic air can descend in unpredictable ways. And it's almost serendipitous that this NOAA image has that cold air descending right around the Great Lakes. But in 2014, that is exactly what happened. So I asked this question to the community: do we have models? Do we have the ability to understand when an Arctic polar vortex or some other phenomenon like this might occur? And to what extent does it affect water level variability in the future? And then finally, I want to finish off with this idea that we are looking to extend our research more globally. A couple of years ago, I launched a research project with the Malawian government, and in particular, the Department of Fisheries in Malawi, to better understand the Malawi water level variability and to develop a water level forecasting system for Malawi and also for the Shire River, which drains out of Lake Malawi. They are interested in particular in fisheries management as a major source of protein for the country, and also hydropower generation. So part of that trip involved traveling along the Shire River and understanding how they're diverting water off the Shire River down across the countryside through tunnels like this one that go into subsurface turbines to generate electricity for a large portion of the country. As soon as COVID dies down, we're planning on returning to Malawi to help develop a water level forecasting system for them that can help them improve hydropower forecasting and also understand how water level fluctuations impact the fisheries management. So with that, I want to thank Wayne State. I want to thank Jamie, Delashon, and Tim again for helping put this all together. And I want to give one more shout out to our sponsors and our funders for this work. Thank you all for your time and attention. And I'd be more than happy to answer questions and continue the discussion. So thanks again.
Thank you, Drew. I think we'll just wait a minute here and see what kind of questions come in. Jamie, are you seeing questions come into the chat? There we go. Okay, Drew, we've got first question here, and it says, are there any explanations for the increased over lake precipitation, and can climate models help predict what happens in the future?
Yeah, great question. So as of right now, I have spoken with a lot of my colleagues. So I am not an atmospheric scientist, although I have a lot of respect for and try to work with atmospheric scientists and climate modelers. I have not found anybody who is doing regional climate modeling who has identified a model that has been able to reproduce this phenomenon. In other words, been able to say, hey, we have a model that shows that the increased amount of water that came into the Great Lakes came from the Gulf of Mexico, or that it came from the North Atlantic, and that the increase in flux was due to, let's say, a change in circulation pattern. I do know that there were intermittent storms in 2017 and 2019 that led to a lot of the flooding on Lake Ontario that were directly linked to an increase in moisture coming up from the Gulf of Mexico. But when it comes to this entire period, almost a decade of extraordinary influx of precipitation to the Great Lakes, I haven't found a model who's been able to fully explain it. And that's a really important research question to see if we can untangle whether this is a major shift that has happened. Do we expect this to continue in the future? So that's sort of the short answer to my question. It's something we need to keep looking at.
All right, thank you. The next question here is about any thoughts on how lower groundwater levels will affect the Great Lakes water levels?
So great question. That question might be referring back to one, I won't go all the way back through it, but to the original question about depletion in groundwater. So if we think about groundwater, it's important to recognize that groundwater actually can have several different layers to it, separated by impermeable earth or sort of clay or rock. And it turns out that the groundwater lens or layer that Joliet was drawing from has been depleted, which is a little bit different from the sort of the overall highest groundwater table surrounding the Great Lakes. So in fact, while the Joliet lens that they were drawing from the groundwater layer has been depleted, the surface groundwater is actually part of a separate layer, and that is closely connected to the lakes themselves. So it's a very complicated problem, and I'm not an expert in it, but that's part of one of the things we're trying to resolve with the USGS Powell Center project.
Okay.
So I guess one more way to answer that is that the rate at which some of these deep subsurface pockets of groundwater are being depleted is very different from the rate at which groundwater is being extracted from the surface groundwater layer. And it's important to understand that distinction in terms of our future planning.
Okay. The next question brings us back to this idea of glacial isostatic rebound. And we're wondering, will the long-term impact of glacial rebound be more St. Lawrence flow as the basin becomes shallower, assuming constant precip and evap? What about spillway incision rates on the St. Clair or the Niagara River?
Okay, what a great question. So just to help, maybe help re-articulate the question for me and maybe for some of the audience, the idea of as isostatic rebound, as the Great Lakes Basin, the land surface is sort of rotating, I think the question has to do with, is that changing the rate at which water is actually flowing out through the system? I think that some people have actually quantified that during some studies where people looked at increased flow rates through the Detroit and St. Clair River and attributing changes in the flow rate through that channel over time and differentiating among isostatic rebound, climate change, and also anthropogenic changes to the channel. I don't know how the scientists who came up with the result directly attributed isostatic rebound to that change in flow, but I think the question is a really important one that I don't have a great answer to. I will say this. Well, first of all, it's a great research question. I think we need, as a region, to have a better answer to it. In other words, how is the tilting of the land surface changing the way that water might be flowing through the system, particularly through the channel right here, through Detroit and St. Clair? I do want to mention that some scientists at the Jet Propulsion Laboratory recently published a study that is closely related to this. They actually documented something fascinating, which is that the Earth's crust beneath the lakes during this period of high water levels actually got compressed to such a point where there's actually been a change in the overall volume of the lakes. In other words, there was so much hydrostatic pressure due to this high water level period that there was compression in the earth underneath the lakes. The lake surface elevation stayed the same because of hydraulics, but the overall volume changed. I think there's sort of an interesting side point that someone made to me recently, but This idea of the isostatic rebound affecting flow rates through the system is something that I think needs to be studied more, and I don't have a good answer to that question.
Okay, thank you. The next question here is regarding your groundwater project, and the question is wondering what models you're considering to use to study the groundwater contribution to the lakes and the water levels.
Yeah, fantastic. So let me just pull this up here for reference. So the short answer is any models that people might be willing to bring to the table. Initially, we were going to try to develop a coupling between WRF Hydro, the weather research and forecasting model hydrological subroutine, which had been developed by NOAA and by the National Center for Atmospheric Research, NCAR, for the entire country and also for the Great Lakes Basin. And we were going to try to couple that with a conventional subsurface model like mod flow and or GS flow. What we've done instead is we have recognized the complications there, and my postdoctorate fellow Yuen Mei is almost working exclusively right now on trying to customize mod flow and GS flow to the entire Great Lakes Basin using some stratigraphy data provided by Ed Siddiqui in Canada using some output from their model they recently ran. So the short answer is right now we're focusing on mod flow and GS flow and customizing it to the entire Great Lakes Basin, although we're open to other models as well.
Okay. The next question is about evapotranspiration and how do we go about getting measurements on that sort of thing?
Yeah, great question. So, you know, if you really want to know, this particular paper that we just published has a documentation of how we came up with these evapotranspiration estimates. In general, they come from land surface models. The broad scale estimates come from land surface models that are calculating the total amount of solar energy in, the amount of water available for evapotranspiration, and the amount of energy that goes into heating the water and causing it to evapotranspirate along with vegetative cover. But it's important to note that a lot of these, on a very, very local scale, we could use eddy covariance meters or other flux measurement techniques to understand ET on a very local scale. The broad scale data sets that we're looking at on this image in the top panel B, and for other basin scale estimates, were you probably in general and in this study using a combination of models and model simulations that have at specific points across the landscape been either calibrated or validated to in situ monitoring infrastructure when and where it's available. And that's the case here. In this particular case, we combined several different data sets, including one that was developed by our colleague Ben Livna, who's now at the University of Colorado Boulder. He did his PhD work with Dennis Lettenmeyer in the University of Washington and developed a pretty comprehensive data set of land surface fluxes across the greater part of Northern America. So that was one data set that went into this particular study.
Okay. The next one is any thoughts on how long you think Lake Michigan will continue to rise?
Would love to talk with some of my colleagues about that one. Let's take a look here real quickly at Lake Michigan, Lake Huron, and if I could pull up a more recent data set, you know, Lake Michigan, Lake Huron look like they're actually going down just a little bit relative to where they were last year, but I don't spend as much of my research looking at the month-to-month, year-to-year patterns as I used to. But I don't think we have a really great answer about what has been driving the precipitation flux into the Great Lakes over the past several years and whether that is likely to continue. I haven't found any scientists who are willing to talk about that. And we really can't answer the question about water levels staying high or even getting a little bit higher until we can answer the question of whether or not this influx of precipitation to the region is likely to continue. So I don't have a great answer to that question, but it's a good one.
Okay. The next one is there were calls for filling the sinkhole in Lake Huron. How much worse would flooding be now had that happened?
Huh. Yeah, that's a great question. So, right, there were calls for filling the sinkhole. And I think what the question is probably alluding to is that in the historical record here, there have been calls for anthropogenic controls to mitigate against low water levels. And just to contextualize the question, there were calls for anthropogenic controls in the mid 1960s to keep water levels from continuing to go down. And there were calls again for some of those in 2012 and 2013. The most common approach was to look at sort of these flap gates that could be put in the bottom of the Detroit and St. Clair rivers to artificially slow down flow. I don't remember, and I don't have enough understanding of how those were designed to know if they were sort of a permanent fixture that would permanently raise water levels a certain amount, or if they were designed to adjust over time and could be lowered. If they were designed as a permanent fix, certainly water levels across the system would have been raised that much higher. But I don't know if they had a sort of a tuning mechanism in them. Nonetheless, they weren't installed. So the short answer is that any permanent alteration of the flow rate through the Detroit and St. Clair rivers that would have permanently raised water levels would have caused water levels to be even higher than they are right now in principle.
Okay, thank you. Is there a periodicity in the water levels? We saw this in the Detroit River water discharge levels for the past 100 years.
So I have not spent a lot of my time and my research doing independent work on studying periodicity of water levels. I've seen papers that I haven't fully sort of unraveled that argue that there's a periodicity in water levels. And I know that you can do anything from looking at the water level cycle like this and saying, oh, look, they come in 30-year cycles by just sort of moving your finger up and down, to more robust and quantitative approaches. But I guess the best way to answer the question is I haven't independently done any of that work. Although I am a little bit, I'm interested in what would be driving those cycles. For example, is there some large scale climate pattern that would be driving 10 or 20-year cycles in precipitation that would then propagate into water levels? I'm not sure why water levels in and of themselves intrinsically would have some cycle unless it was being driven by changes in the rate at which water was coming into the system. But I must say, I'm almost embarrassed to say that I don't have a really good understanding of those multi-decadal cycles in precipitation, and I'd like to study it more.
Okay. Any advice for the coastal community trying to reduce risks in the face of water level variability?
Don't build houses near the shoreline, or don't build expensive commercial properties near the shoreline, because if we look at the water level record over the past 10 to 20 years, it's very likely that water levels are going to be high at some point, and it's likely that they may at some point become low as this sort of tug of war continues. My personal opinion, which doesn't represent the opinion of any agency or university, is that most of the coastal land should be set aside for the public good, and that you run an incredible risk if you try to encroach private or commercial property right along a shoreline, especially if it's a sandy one susceptible to erosion.
Okay. And given the importance of uncertainties in the connecting channel flows, what's the impact of water level regulation, specifically in the St. Mary's River and Lake Ontario?
What's the impact of water level regulation? So I'm going to borrow words from some of my colleagues who are on the phone here, including Tim Calapi, but other folks who are from the Army Corps of Engineers and NOAA, which is to basically point out that the controls at the outlet of Lake Ontario that control the rate at which water goes out have a significant impact on water levels. If we look at this plot right here, we can see how in general, the magnitude of monthly water level variability has diminished a lot since the implementation of those control structures. Although we can also see that there are limits to what that outflow control can do, particularly in 2017 and 2019, where despite having that control measure in place, there was so much water in the system that Lake Ontario hit record high water levels in 2017 and 2019. So that's my response to the story about Lake Ontario. I would argue that the control structures on the St. Mary's River that control in part the outflow from Lake Superior, I would first point out is that there are many other experts on the use and the control of those systems, many of whom work for Environment and Climate Change Canada or the U.S. Army Corps of Engineers, and I can't speak on their behalf. But what I can say is in general is that the impacts on water levels through those control structures are very minimal over the long term, and nothing like the control that they have further downstream on Lake Ontario.
Okay. And thinking about predictive capability and resiliency, how can this data set best be used?
Let's see, I'm sort of trying to think about when the question asked this data set, I'm trying to think of which data set.
How can we best use this data? I'm thinking about predictive capability and resiliency. My guess is here it's just the hydroclimate data that you've got.
Yeah, yeah. Well, so one of the ways, let's in terms of looking to the future, there are different approaches and different timescales that are important to consider. If we're looking at seasonal to interannual projections of water levels, the historical data that our group generates and that other groups generate is extremely important because it captures relationships, or if you will, correlations between precipitation, evaporation, and runoff. And if we can use the historical data and the relationships between those variables and propagate them into the future, we can have a much better understanding of the range of water level variability into the future. And we can also look at ways to maybe manipulate certain aspects of the historical record that are consistent with the future of climate change. For example, a slight increase in precipitation or a corresponding increase in evaporation at certain times of the year. It can become somewhat simple to run through what we call plausible scenarios of future water levels if we can view the historical water balance record and then project it into the future. If we start looking at water levels at much longer timescales, sort of multi-decadal timescales, the story becomes a little more complicated. So I'll stop short on that one when it comes to taking historical data and looking forward at monthly or just interannual timescales.
Okay. The other part of this question is MDOT is a sponsor of this work. How does MDOT use these data?
So the Michigan Department of Transportation is in general interested in how susceptible coastal infrastructure might be to variations in water level. And so this is almost like a coastal inundation question, is sort of looking at how are long-term water levels fluctuating, and then how are storms and storm surge added onto that water level variability, leading to potential changes in design of nearshore coastal infrastructure, including roads and bridges.
Okay, so Drew, we've got about 10 or 15 more questions here. This can be completely up to you. We can keep going through them, or we can have them sent to you to answer and reply, and I guess get posted with the presentation here.
Sure. The reality is that I have time, and I'm more than happy to stick around and go through a few more questions if people want to pose them and have them answered while I'm talking. So if that's okay with the moderators, I'm happy to do so.
Okay, sounds like it's up to you. So we'll keep rolling here. So how can we use this data to address diversion requests and demands?
Wow. Okay. So yeah. Okay. Now we're getting into the real stuff. Okay. So, so just so everyone understands the context of the question here, the Great Lakes Compact is one of the agreements that sort of says, hey, in general, we cannot divert water out of the Great Lakes Basin, but as many of you know, there are requests for exceptions to the compact to allow diversions of water. The Waukesha diversion is one of the best examples. But I show this slide just to put into context some of the diversions that have been historically, I don't like the term, but grandfathered into the compact, one of which is the diversion of water into the Great Lakes Basin through the Ugoki and Long Lake diversion. That's represented here. And then the diversion of water out through the Chicago diversion. Okay, the question is, how can this historical data be used to better understand diversions? It's absolutely critical to understand the flow of water coming into the Great Lakes and leaving the Great Lakes under natural conditions over here on the left, in order to understand what the impact on the overall water supply might be through a diversion of a magnitude like this one. If you don't have the context of the water balance components and you don't have those uncertainties quantified really well, it's really hard to understand what the potential impacts of the diversion of a certain magnitude might be, And in fact, this is one of the biggest problems that people say plagued the Aral Sea and other large water bodies around the world, where they were not able to differentiate the impact of diversions, in many cases for agricultural use, from climate change. And so one of the things that motivates our research is being able to continuously say, hey, this is the amount of water lost through evaporation, this is the amount of water coming in through precipitation, and here is how much is being lost through either diversions or consumptive use. So having a strong historical record of these water balance components, I would say, is absolutely critical to supporting not just things like diversions, but the overall integrity of the compact.
Okay, we've got another question here about isostatic rebound in the northern part of the basin around Lake Superior. For example, it led to significant changes in relief or increased flow through the systems. And is it expected to? Is it expected to increase flow through the system, I think is what the question is trying to get to. And
okay, I think I understand. Is it expected to lead to increased flow through the system, right? I guess that's the question.
Yeah.
So I'll answer that question in 3 ways. The first is I am not an expert on isostatic rebound or its impacts on flow. Okay, so I am not the expert. But the second way I'll answer that is that I'm curious about that question, and sort of hypothetically, it's reasonable to think that as the basin is tilting in the way that we see here on this screen, that it could have an impact on the relative elevation of water and how water is flowing through the system. So that's the second way I'll answer the question, although I can't confirm that, but it does seem like a really strong hypothesis that should be tested. And the third way I'll answer that is what I mentioned before, is that somebody, as part of one of the recent Upper Great Lakes studies, attributed changes in flow in the Detroit and St. Clair River system to 3 key things: climate change, changes in the channel conveyance, and isostatic rebound. I don't know the background on how they did that, but somebody already said that changes in isostatic rebound are leading to changes in river flow here, but I don't know the background on where that came to. So I'd love to figure that out, and I apologize that I don't know the answer, but those are the 3 ways I would answer your question.
Okay. The next question here is what type of data is required to help reduce model uncertainty? Is it a function of resolution in time or space, or the amount of new data?
I would say that is a great question. And because what I'm thinking about here is that quite often when we increase the temporal or spatial resolution of a model, which is the trend right now in numerical modeling, particularly with atmospheric science modeling and land surface modeling, we end up with a result that is very deterministic. Maybe we have one sort of prediction, but that doesn't mean we've reduced uncertainty. It means we're representing a particular discrete scenario instead of assumptions. And my perspective is that what happens is when we increase the resolution of numerical models, we're actually coming closer to focusing in on one particular set of assumptions and one particular scenario. And what I think a lot of the studies of future water levels have done, maybe, and I might have a slide here that shows this better. So I have a set of backup slides here. And let me see if I can point this out. What I'm getting at here is the high resolution numerical models that are used for future water level forecasting. Here it is. Okay, so here is an ensemble on the right-hand side of many, many different high resolution models that are translated into water levels in the future. And each one of these high resolution models has a different assumption about how things might play out on the land surface and in the climate. And as you run different scenarios through these models, what you end up with is a range of water level outcomes that is not that different from the range of historical water levels in the historical record. And so I'm not particularly convinced that super high resolution models are necessarily reducing uncertainty. I think they might actually be masking uncertainty. And that when you have simple models where you are able to express uncertainty in a model parameter well, you might actually have a better representation of uncertainty. That's sort of my hypothesis, and maybe too long-winded answer to the question.
Okay, Our next one here is what's being done for depleted groundwater management to contain public trust resources to protect areas staying within local water available?
Yeah, that's beyond the scope of what I study and I'm able to comment on. So I don't know what measures are being taken to do that. I'm sorry.
Okay. Uh, how much control do we have about cutting off flow of the water between the lakes as the water flows to the St. Lawrence?
Cutting off flow. The short answer is not much. The amount of water flowing through the lakes is extraordinary. If we get back to this image right here, these are continental scale flows, right? If you remember that the Mississippi River has an annual average flow of about 18,000 cubic meters per second. You really can't shut these flows off. The most that can be done is really what happens down here at the outlet of Lake Ontario, where a massive dam can slowly back up periodically or just slow down the rate of flow or change the rate of flow, but it's certainly not, it's not feasible probably to stop these flows. They're just of too large a magnitude.
Okay. The other one, next question here is, can you speak to lake temperature records and if you've used those overlaid with your water balance data to see if there's any correlations?
Yeah, absolutely. So a couple points I can make about that. So first off, yeah, temperature is extraordinarily relevant in the lake surface, in the lakes to this question. So here's an image that comes from a paper we published, taking a closer look at what happened in the late 1990s. So here, this was published in Science in 2014. So on the bottom of the plot here, here we have water levels, where the story sort of starts. The green bar right here represents the water level anomaly on the Lake Michigan-Huron system. The light green bar is the water level anomaly on Lake Superior. You can see water levels going along this rapid decline right here in the late 1990s. Letter A and letter B represent months where record low water levels occurred. So the next phase in the answer to this question is, okay, what was happening with the water balance? And I think I showed you earlier that there was a huge surge in evaporation during that time period. So again, the darker line is Lake Michigan-Huron. The lighter line is Lake Superior. Surface water, lake evaporation going along, and then significant and sustained rise. You can see this period of sustained and high evaporation relative to the historical record. But then finally, the sort of driving mechanism there was the increase in surface temperature. So here's a look at long-term surface temperature records for each lake. Again, the darker line, Michigan, here on the lighter line, Superior. A lot of science has been studying changes in surface temperature across the lakes. But what's fascinating is this rise right here in the late 1990s, almost a 2 degrees Celsius jump in the surface temperature of the lakes that was sustained throughout this time period. So a jump in surface temperatures, a jump in evaporation, and a decline in water levels that occurred during that time period. But one additional point I want to make is that this is just looking at the surface temperature of the lakes. My colleagues at NOAA and I just published a paper that was in Nature Communications, led by Eric Anderson, that took a closer look at what's happening under the surface of the lakes. And it turns out that the NOAA Great Lakes Environmental Research Laboratory had a long term of subsurface measurements on what's called a thermistor chain. They could allow us to integrate what's happening across the entire water column. This paper was just published, and the most compelling image from that paper that I think is this one right here. It's showing the average trend in temperatures in Lake Michigan across the seasons and across time. What most of us are looking at, and we were looking at in that previous plot, is just the surface. So this axis right here is showing depth. The horizontal axis is showing time. And so if we just look at the surface, we see this warming trend in January, February, March, April. All these colors are indicating the rate of warming relative to cooling. But what we found fascinating is this is a troubling trend if you're concerned about temperature. This entire pocket of water here, January, February, March, and April, down at depth below the surface is showing a profound warming trend in Lake Michigan. And this is going to have long-term impacts in terms of turnover of the lakes, the overall lake heat content, that eventually will propagate into changes in surface temperature as well as evaporation in the water balance. So great question, and this is sort of the long-winded answer to it. And Tim, I know we're at 3:43 here. I'm okay if we take maybe one more question, and then if people want to contact me or any of the other experts on this field, it would be great to continue the discussion. But Tim, maybe I'll take one or two more questions and then we can wrap up.
Okay. This is a good one here. Talking about lake-to-lake flow, and how do we improve those flow estimates? Do we need measurements, models, or something else?
Okay. How do we improve those flow estimates? So this is in fact what our project with Tim and others at the Army Corps of Engineers is focused on. How do we improve these estimates? Well, one way is to continue advancing the monitoring infrastructure, right? There are several different ways to monitor flow in rivers and streams, some of which involve things like old mechanical flow meters. And for a lot of the historical record, that's all we had. But some of the new techniques involve things called ADCPs, acoustic Doppler current profilers, or current meters that can provide a more sort of accurate reflection of what's happening in the water column. Those are being put online right now. But I would argue, even with those measurement techniques, there are still some uncertainties and variabilities. Another approach that we're taking in partnership with Tim and the Army Corps and a lot of other people who are using this technique is to use this picture, use the entire water balance of the lakes to get an understanding of what those flows need to be. And so I find it helpful to think if you can put all that information together, these different monitoring techniques, the overall water balance, those can help us give a better idea of what the flow is in these massive, massive channels.
Okay. All right. Well, thank you, Drew. Thank you for your time. I wanted to, before we all go here, I wanted to let us know what the next water at Wayne would be. I think Jamie, I don't want to say it wrong, and my screen went away with that information on it. So I think it's was it May? I don't want to say the wrong date, Jamie. Is it? Can you throw it in the chat for me?
I just put it in the chat.
Okay. I think it's May 6th with Dr. Frida Gilbin, and she'll be discussing water in art at the DIA. And also, just as a reminder for anybody that maybe came in late or wants to see any of this presentation again, it was recorded and it will be available on a website, and we'll send the details out on that a little later. And thank you all for attending, and thank you, Drew, for the presentation.
My pleasure. Thank you.